All right, so we're going to discuss electronic spectroscopy again, except this time the topic will be the Frank-Cunnin principle. Okay, so as an example, I've drawn two electronic curves, one for the ground state, one for the excited state, of the same multiplicity, spin multiplicity. So what we're going to do is look at the intensities of these transitions. All right, so the transitions from v equals 0 on up are mostly vertical. But note where on the excited state curve it crosses. So it does, if it's vertical, it kind of misses this thing entirely. Okay, so in the excited state, the range of vibrations for v equals 0 is way different than it is for the ground state. So basically, what you have to look at is the overlap of this vibrational wave function, which is a Gaussian, with this one, and that's actually going to make your intensity go almost to 0. Okay, and what's commonly done with some of these figures is actually to draw the spectrum on the side. So this would be a transition energy of 0, and then if you go from here to here, this would be the e to the 0 to 0 transition from 0 in the ground state to 0 in the excited state. And basically, there's no peak there. Okay, let's continue going up in the energy levels. In v equals 1, it's a lot closer, so maybe there's a little bit of overlap, but not too much. So maybe just a little bit of the range of the distances overlap, and so maybe you'll see a tiny little peak. All right, and then when you look at the vibrational wave function for v equals 2, there's better overlap, so you get a more intense peak at this energy difference, which would be something like this. And then continue on. And so as you go up and start to overlap, as these vibrational wave functions start to have a distance range that kind of overlaps with this distance range, the overlap of the vibrational wave function improves, gets larger and larger, and so the peaks are more and more intense. And maybe the most intense peak should be this one here. And then you would see this. Okay, so this is called a vibrational progression. Where this is a very famous sort of phenomenon where you see lots and lots of peaks because you're exciting to lots and lots of different vibrational levels for the excited state. One of the more famous examples of this is molecular iodine. And the reason iodine is so famous is because it has like about 100 vibrational levels in the excited state. So you see many, 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 many peaks. So when you look at the vibrational progression of I2, you can see there's kind of like a limit here, past which you really don't go. Okay, so that's the energy difference where you stop seeing the absorptions occur because the excited state molecule is now completely broken apart. So if you're actually to plot these as a spectra, you see lots and lots and lots and lots and lots of peaks. As a matter of fact, seeing the 0, 0 peak is probably almost impossible because I2 has such a low vibrational ground state vibrational frequency that actually you can have some v equals 1 vibrations in some of the molecules. And so now you start to see excitations from v equals 1 on up here. And these would be at shorter wavelengths, or sorry, longer wavelengths. So you'd see another series of peaks kind of mixed in. And actually there'll be a third set of peaks for v equals 2 going up to these upper levels. But anyhow, the spacings in these peaks are going to be more or less the spacing of the vibrational frequencies of the excited state. And so this is called a vibrational progression, because you can see that there's a series of the regularly spaced peaks. The other thing is the intensity pattern is given by something called the Frank-Cunnin principle, which says the vibrational wave function overlap determines the intensity. So the more that this little wave function drawn in pink, this Gaussian function, overlaps with one of these little pink either Gaussian or Gaussian times Hermite polynomials for the vibrational wave functions. So since these curves are offset, the best overlap occurs at the edge of this curve where the vibration starts to compress and then turn around and then stretch and then come back. So the bigger the overlap here, the more intense the peak is. So if you see a pattern like this, then you would assume that whatever vibrational quantum numbers these correspond to, that corresponds to closest to a vertical transition from the very center of the molecule right here. All right, so that's the Frank-Cunnin principle.